Hello everyone, today let's solve the problem number 701, insert into a binary search tree. Right, so what the question states here, we are given the root of the binary search tree. You can clearly see here, the condition for the binary search tree is the left node, the left subtree or the left node has to be this one. The value of the left node has to be lesser than the main node, and the value of the this one, right node, this one 7, where I'm pointing the mouse, right? So the value of the right node has to be greater than the main node, right? So same goes with every other this one main node. If we consider this one as the main node, so this one has to be lesser and this one has to be greater. So then only it is said to be this one, what we call binary search tree, right? So we are given the root of the binary search tree and a value val to insert and a value val. So we have to insert 5 in this case accordingly with the question, right? So we have to insert val such that the resulting tree remains a valid binary search tree. We have to insert val such that resulting tree remains a valid binary search tree, and we have to return the root node after insertion. We have to return the root node after insertion. It's guaranteed that val does not already exist in the tree. It's guaranteed that val does not already exist in the tree. Val does not exist already exist in the tree. So we have to return the root node after the insertion, right? So we have to insert the value 5 and we have to return the root node after insertion. And also it's guaranteed that val does not already exist in the tree. Means 5 will not be given already in the tree. Every for every input, val does not exist already in the tree. That's what they have given in the question. So let's come to the first part here. I mean first example, sorry. So here you can clearly see we have 4 2 7 1 3 and we have to insert 5. We can insert 5 at the end here. This one right node, this one doesn't have, accordingly with the binary search tree the value has to be smaller, so we can insert here. Or we can do one thing, we can insert 5 here, we can insert 5 here and see. I'll just show the this one figure itself. Same here, they have done the same thing here. We can insert 5 here and 4 we can insert at the right, not left, right? So this has to be, 4 has to be greater than 3. This is binary search tree, right? So this also we can do. So overall output would be 427 135, 427 135 after inserting. So let's come to the second example. Same thing, man. Same thing, you just check it out and just draw the binary search tree and just check it out for this as well. So we are inserting 25 here. So see here, we are inserting 25 here. We are inserting 5 again here for the third one. So last one you can clearly see we have inserted 5. We have to insert 5 basically. So after this one, the output that we need to get for example 2 is this one. For the example 3, we get this one, 427135. So I hope the question part and example part is completely clear, right? So I hope the question part and example part is completely clear. Now let's discuss the approach very quickly. Now let's discuss the approach very quickly. Let's discuss the first, let's consider the first example for the approach. Let's consider first example. Root we have been given this one, 42713. Value we have to insert is 5. Value we have to insert is 5, right? So let's do one thing. Let's start at 4. Let's start at 4. So we have initially 4, right? Let's start at 4. So here we will start at root 4. So one thing we will check here is we have to insert the value 5, right? 5 is greater than 4. 5 is greater than 4. 5 is greater than 4. So what we will do here in this case, so we will go to the right child. So we will go to the right child, nothing but 7. So we'll go to the right child, nothing but 7, right? So at node 7, again we will check whether this one, we'll check with the value that they have given. Again 5, we'll check with 5. So 5 is lesser than 7. 5 is less than 7, right? So we will go to the left child of 7. This one is null. Left child of 7 we have been given null, so we will insert 5 here. So we will insert 5 here in this case. So we will insert 5 here. Other nodes remain same. Other nodes remain same here. Here this one will be 2 and this one, this 2 consists of 1 3. This remains same. So here first we will compare with 5 basically. First we will compare 4 with 5. This is lesser than 5. 5 is greater than 4, but we already have 7 in the this one, what do we call, right node. Accordingly with the BST, right, this node has to be greater and this one has to be smaller, uh, greater or larger, right? So this one has to be larger, but here in this case 7 is already greater than 4 we have. So we will again uh, check 5 with the 7. 7 is less than this one. 7 is greater than 5. So here we can insert 5 at the left. We will check whether the left node exists or not. Left node is null and we can insert here. No number exists here, so we can insert 5 here. So we will be inserting 5 here, right? Or we can go with this one as well. This one as well. This is accepted as well. So this is fine. I hope this part is completely clear, man. Very easy to understand, right? So we will be inserting 5 as the left child node of 7. Left child node of 7. So the output after inserting would be 4 2 7 1 3 5. The output that we got here is this one, which is equivalent to the output that they have mentioned for the example 1 in the question. So our approach works absolutely correct in this case, right? Our approach works absolutely correct in this case. Now as we are done with the approach part, let's discuss the this one complexities part very uh, yeah, let's discuss the complexities part quickly. So here what would be the time complexity? The time complexity would be big of h. The time complexity would be big of h. So why it is big of h? H is nothing but the height of the tree here, right? So basically it is logarithmic n for the balanced tree and big of n for the skewed tree. So it is better to go with the big of h rather than considering balanced or the skewed tree for the worst case, right? So let's consider the height of the tree instead, right? So this is big of h. So sorry, yeah, I'll just write it in the small h. I'll just write the small h here. So the space complexity would be big of h as well, because we will be making use of the recursion, or recursive call stack can go up to big of n, or we can just consider the tree height. Due to the recursive call stack up to the tree height, it will be big of h. So this would be space complexity and this would be time complexity. So the time complexity and the space complexity for the code that we'll be writing in the future would be, for both it would be big of h basically. Now as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code. So the first part here would be, if the tree is empty, we have to create a new node with the value and return it as the root. So here if root equals null, here if the root equals null, then we have to return new tree node of val, new tree node of val. So this is fine. The next step, if the value is greater than the root, then we have to insert that one to the right subtree. So this is binary search tree, right? So we have to know what is binary search tree, right? So if the value is greater than root, then we have to insert an right subtree. So I can just write the simple if condition here. If value is greater than root dot val, then what we will do, I'll just give root dot right here. This one will be insert into bst. This one, let me consider this one and let me paste it over here. Insert into bst. This one will be root dot right comma val. This is fine. Else what we will do, else if the value is less, then we have to insert in the left subtree. So I'll just copy this one and let me paste it over here. Let me paste it over here. So just give me a second here. Instead of this one, let me make this one root dot left. So into bst, this one will be, we are going with the recursion, right? Root dot left comma value. Means if the value is less, we have to insert into the left subtree. We have to insert in left subtree. Finally, we are left with one thing. Means we have to return the unchanged root node finally, right? So we have to return root basically. So I'll just come here. Let me return root. So we are done with the code. So as we are going with the recursion, the code is pretty much easy, right? So the code is pretty much easy to write. So this is fine. Let me hit the run button. This is it for the code. All right. So you can clearly see here the sample test cases are getting passed. So let me hit the submit button quickly. I hope this works for all the test cases. Yeah, you can clearly see here all the test cases are getting passed. Means the code works absolutely correct on this case. The code works absolutely correct on this case. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.